Yeah, I'm sharing. Nothing today greater than IMO 3. All of them are very doable. Uh, Two of them are less than at least. Yeah, okay. First three are not IMO 3 level even. Fourth is close to IMO 3 ish, I guess. I don't think so though, but Giori does. Mm, first three, I wouldn't say greater than IMO 2. Fourth, maybe, yeah. Okay,
Are all these greater than IMO 2?
no, these are just buffer problems. For the ones who are familiar with the content we are doing, they can try the problems meanwhile, and while I'll explain the content to the others. Whenever they think, okay, now there's something helpful for me, they can also start listening and focusing on the lecture. So that meanwhile, everyone has something to do. Nobody's getting bored or something. Sounds fine? Sounds good?
Yeah, okay.
Okay. So I told everyone to be familiar with what inversion is. So I'll assume that you know what inversion is, but I'll still tell you once.
Okay, so I don't know what inversion is.
Okay, no issue. I'll just tell you what it is, but you'll have to prove the basic results on your own. I'll just tell them to you. After content, we'll be able to solve these in reasonable. Depends. You'll still need practice. These are not direct easy problems. Okay, so let us start now. Inversion is basically this simple idea that you have. Is the okay? Is the GeoGebra visible?
Yes.
Yes. Yes.
That you have some circle and you. Okay, sorry, somebody joined. Yeah. So there's some point in this circle. Let me hide B. Yeah. And now the inverse of C in this circle is simply okay. For those who are just joining once, okay, my bad. These are the buffer problems. The link to the read link is in the chat. If you know the content, do the buffer problems. Okay. For the ones who are not familiar, you have a circle and you have any point in the plane. Now its inverse is defined as the point C dash such that AC into AC dash is R square, where R is the radius of the circle. That's it. Okay. That's all there is to inversion.
Yeah.
By
So
definition.
inverse of some point is defined.
What?
Okay, wait. Okay, so let me type in the chat, and then I will change my headphones. Fine.
Inverse of every point on the plane is defined except, of course, C equal A.
Okay, fine.
Inverse of every other point is defined.
Isn't the inverse of a point at infinity?
You
By
don't.
definition.
The point of at infinity does not really exist, but that way, right? Like the point. It's not. If you're working on the Euclidean plane, there's no point at infinity.
Yeah. Yeah, but in the extended plane, uh,
If you
you can
extend it,
say,
if you can extend it, then you can say all of those come to A.
yeah.
But that's just unnecessary. Okay. Now important part. First property. If I have 2 points like this, I invert both of them like this. You get C dash
So
D dash.
inversion is basically reflection across the circumference of a circle.
Not reflection.
No.
AC into AD dash is R square,
Oh yeah. Okay. Sorry.
not reflection. Reflection would only make sense when the point is on the circle.
No, right. Actually, I was asking because, like in GGB tools, you are doing transform. like in transform, you're doing reflect about the circle.
Yes, that does not, that is the name of the tool, but that does not mean you're literally reflecting across the circle or the circumference. That's, this transform is also called reflection about a circle, but that is defined this way. That is not normal reflection, is the point.
Okay.
So if CD go to C dash and D dash, then C dash D dash is a cyclic quadrilateral, is your first property. Again, this is just direct because AC into AC dash is AD into AD dash is equal to R square. So this is cyclic quadrilateral by power of point. That's your first property. Next we just have that, okay, where is this? Okay, why did I remove the circle? Yeah. If you have a line, random line, if you invert it, it goes to a circle passing through A or your center. Okay, this is for you to prove. Next you have, if the line goes through A, the line inverts to itself. A circle through A inverts to a line. And okay, sorry, people are joining.
Also, our points of inversion defined outside. Like I don't think so.
What do you mean points of inversion?
Like no. Like a inversion of any point outside the circle is not defined, right? Or is it?
No, of course it is. Like you're simply saying AC into AC dash is R square. The point can be anywhere.
Okay, so I think this comes from if we apply a property from for C and D both, and then we'll get like that this circle will pass through A.
Yeah, you have to prove it. That's not something I'm discussing.
Okay.
Okay, this is your property, and the last property is if you have a random circle, it also inverts to a circle. These three properties are very basic and you should just know and be able to easily prove them. A random circle goes to a random circle, a circle passing through A goes to a line, a random line goes to a circle passing through a line through A goes to the same line. Cool, these properties are fine.
Yeah.
And a line passing through the center of the inverse of CD, then the lines. What? In passing through the center of the inverse of CD, then that line. Okay, sure. But that's something you have to prove. That is true, but yeah, you have to prove it. Anyway, these are the most basic properties about inversion. I've written these here. You can read. Okay, this is also called Klein's glow to Klein's because circles and lines. So you can see these properties. What's interesting is this is not true for random conics. Please do not say that random conics go to conics. That's just not true.
So what do you mean? Can we apply inversion to conics also?
You can apply. They'll just behave weirdly.
Okay.
You should know this. You should know this property that they'll behave weirdly.
Yeah. Like I have heard that this
No.
rectangular hyperbola transform to Bernoulli's limit state. So
Yes. That's literally your profile picture. That's what I was saying.
yeah. Yeah, right.
For example, this is and let me draw 1 second. Yes, this is your hyperbola x square minus y square equal 1, and this is your random circle. if you do the inversion, you can clearly see it's not very much a conic, and it's the thing in the picture, in his profile picture. This is the diagram that you have.
Yeah.
Okay.
Okay.
So do not do inversion with random conics. They'll not behave as you are expecting them to. They still do behave well if you have some conditions, but not directly. Are these things clear till now?
Yes.
Yeah.
Okay, let's look at an example. First, a classic example, then I'll share a few nice inversions. This classic example is the shoemaker's knife. How many of you have seen this before?
In APMO, I have.
I have.
Uh, I could not hear. There were a couple voices overlapping. Can you repeat?
I have seen.
Okay, good.
Yeah, I also have seen.
Okay, nice. Okay, I need another point. Okay, can anyone tell the statement now?
Yeah, like I've seen there's a very good video of number file on this.
Okay. I think so. I've seen it, but I'm not sure.
Yeah. He constructs the whole figure on a very big paper.
Yes. Now, does anyone know the statement of what we are to do? Let us construct the shoemaker's knife the correct way via inversion. You take a line, you take, let's say, a perpendicular line. Okay, not here. Yeah, here. How do I hide this? Okay, good. Sorry for the time I'm taking. Just give me a minute. How to draw circles hard.
So all of those properties you told are in your hand, like that handout, right?
Yes,
Yeah,
they are
that's
very common properties that you should know. Of course, this. Okay, now we can work finally. There's a reflect about point. Reflect, 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 reflect. What happens if I invert this full figure? If I just make a stack of circles here, what happens if I invert it now from A?
What radius?
Some radius, does not matter. Some radius.
All will go to circles that are tangent to each other.
Yes, and these two lines.
These will go to circles passing through A.
Good.
Like, yes.
And these two lines are parallel, right?
Yes.
So they'll go to circles passing through A, which are tangent to each other.
Tangent, right. Yes.
So there's this property that tangency is also preserved. Intersections and tangencies are preserved under inversion. That's again very easy to prove that you can do it on your own. Let me just do one thing. About point. This I'll do there. Oh, not rotate, reflect. And I guess this one about this one. Yeah. Okay, we got a few more circles. Great. Now that I'll invert, can anyone explain what the structure looks like? One person explained, someone else who understood? Anyone else who understood can explain?
So we inverted what with respect to what?
I invert the whole other diagram with respect to this big circle that I just drew.
No, just before it. Like before you draw the circle, there were two lines drawn. What
Yes.
was then?
There are two lines. We have a line through A. There are two lines perpendicular to these. I have a circle here, semicircle here. Then I drew a circle which is tangent to this semicircle, this line, this line. Then I drew a circle which is tangent to this circle, this line, and so on.
Okay, and then?
Yes. Now, if I invert from A, what will my new structure look like?
So I think
Invert.
there will be two circles passing through A, and these small circles that you have drawn will be in between those, tangent to both, be in between those.
Good. So these are the circles this line goes to.
No, like this circle is what?
The circle you're inverting with respect to.
A.
A is not a circle, A is a point. This is the circle you're inverting with respect to this red circle.
Great circle we are inverting with respect to?
With respect to, yeah. Like you invert with respect to a circle, no? That's what we
Okay.
were doing.
Okay, yeah, fine, got it.
Okay. No, can someone tell? Someone who understood? Sorry for interruptions when you're speaking, but can someone go on?
Oh, so like these will be circles in between these two circles here.
Good.
And all will be tangent, like to both these circles and to the other circle on the, like you can say, right.
There will be an infinite.
And look.
Good. Very good. So you see.
Okay, so that third circle that you had shown, that inverted to itself,
Yes,
was that intentional?
Yes. I drew this circle so that it inverts to itself.
Okay, so center lies on the. Achha, okay.
No, center does not lie here. The center is off.
Yes.
Okay, these are called orthogonal circles.
Yeah. This is orthogonal. That is why it is.
Orthogonal. Achha.
This circle and a red circle are now orthogonal. I drew the red circle so they are orthogonal.
Oh, I see. Okay. Okay, so then inverted circles centers are not inverse of each other.
No.
Okay.
Inverted circles centers behave very weirdly. Never, they do not behave as the other structure of.
Oh, okay, I see.
So basically, like if you invert a circle which is not passing through A, it goes to a circle, right?
Yes.
So the center of initial circle will go to the center of the image or not?
No.
Okay.
It will go to a point inside the circle, but it will not go to the center.
I see.
Okay. But the circle remains on the same line, of course, like the line joining the center and the center of inversion, but no. Okay, so everyone sees what's happening, right?
Yes. Probably.
Okay, so if I started with this structure where I gave you these two circles and this line, and I drew a circle which is tangent to both of them. Then I drew a circle which is tangent to this circle, which is now this. Then I drew this, and then I drew this. Then I kept going on. Then I can say, because of how we drew this, that the distance of the center of this circle is 2 into r. It's like into the number of circles you have drawn before it. 2r into the number of circles that you have drawn before it. This is 1 circle and 2 circles. So this is 4r. This distance will now be 6r, where r is the radius of this circle. Do you see it?
Yeah.
R is the radius of.
If R is the radius of this circle,
Which circle?
this circle, let's say of, okay, let me color it. The green circle. I say R is its radius, okay? And I ask you what's the distance of its center to this line.
Which line? Oh, okay, okay. AE.
Yes.
4R.
Yes, good. But this is true if I even remove all. Okay. No, sorry. Let me be careful about how I do this. I'd remove these lines.
That's what I'm asking you. What are these two lines passing through it?
Okay, let me be more careful, I guess. Just a second. Yes. So you have, okay, even this I have to hide. Yeah, okay. You have this structure, okay, where you have a circle and another semicircle. Okay.
Okay.
Now I draw a circle which is tangent to this, and this, which is this circle. I call it R1. I draw this circle, I call it R2. I call the circle R3, R4, R5, and so on. Okay.
Okay.
What is the distance of this center of this circle to this line?
4R.
4R. Good. Where R is?
The radius of green circle.
Yeah, radius of the green circle.
This. For the orange circle, what will be the distance of its center to this line?
6R.
Of where R is again?
Or the center of that green circle. Oh,
No. Where R is what?
radius of this.
Radius of red circle, okay.
Orange circle.
Oh, sorry, orange.
Yeah. So do you see what inversion did for us?
How did this came by the way? Like 406R.
Didn't you just? I mean, why did you say 4R, 6R if you don't know how it came?
No. You told right now, na, ki, the number of circles you draw before that it will be like that many times, twice of that.
Okay. Don't do that now. Just tell me if you don't know. I'm like, okay. These people, and you got it now.
No. Actually, we just calculated before because of those lines and those circles.
Exactly, you calculated it. That's exactly the same calculation you're supposed to do right now. You have this structure, right? For the
Yes.
orange circle, if you're suppose I'm telling you to find the distance, I do inversion this way, that I preserve this circle.
Yeah, that's what I'm asking. That these two lines are what?
Just the tangents to the circle.
Oh, okay, fine.
Like I'm just, when I invert with this distance, the circle will go to itself, right, by power of point.
Yeah.
Yeah, tangents I hide. Yeah, I take this circle. Yeah, okay, I already do it. And invert the whole figure with respect to it. Now do you see?
Yes.
What? Okay, weird.
Okay, so if you were to invert with twice with different radii, then you'll get homothetic figures. Is that right?
Yes,
Okay, I see.
that's true, but not relevant, I think.
No, but then you can say that it'll be 6 smaller, that one, the radius of that. Because both will be homothetic then. Both
Uh,
figures will be homothetic.
Okay, I don't see why that's true.
So like the original figure had the distance from the line to be 6r, where r is the radius of green circle. Now the distance will
4
be
hours.
6. So, no, I'm
So,
talking about the orange circles distance.
Orange circle
Orange
is 6.
okay. Yeah.
6r, and now because the new inversion had is homothetic to that, so now it will be 6 the in the radius of the smaller circle. So
Sure.
and now
You can
that will be
argue
the,
that way. You can argue that way, of course. But the point is, you can just invert it here. With stick this circle right here. Do not shift it anywhere.
okay.
I invert so that this circle remains. Then everything comes up perfectly, right? This line will go. This circle will have to go here. It will be tangent like this. This circle will go here. It will be tangent like this.
Oh, acha, acha, okay, okay.
Other circles will stack up perfectly like this.
Yeah, so they'll have the same radii as the orange one. Okay.
Yes. And this, your distance becomes R, 2R,
Okay.
3R, 2R,
Mhm.
3R, 5R, 6R.
Yeah, I mean, okay, so like to prove that the radii will be same as well, could use homothetic.
You don't need to do anything. These two lines are perpendicular to this line.
No, like, but acha, acha.
You
Yes,
have to,
yes, 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 yes. Okay, okay, I see.
if you draw any circle that's tangent to both of them, it will have the same
Yeah,
radius.
yeah, I see.
These two are parallel lines. Okay. Did everyone get it? I know it got slightly confusing. So you can look at this diagram if you want. This is by Evan. I, I asked him for the letting, and he was nice enough to provide me the asymptote code. This is your shoemaker's knife, and then if you invert from A, this is how they stack up. What we did just right now. Correct? And now you see why the result follows. You can read the problem now, if you understood.
Yeah, it's that only what you explained.
Yes. Uh, okay. So I hope this is clear. So
So
I'll
this
move.
shoemaker
Yeah.
knife appeared in any Olympiad.
No, this is just a very famous problem, very old problem, and it's a classic example of the power of inversion. You'll see it everywhere. Anyone who teaches you inversion will probably show you shoemaker's knife at some point. It's just perfect, no? Like everything works perfectly, and it shows you how powerful the idea is. You're talking about. You can talk about the radius of the 50th circle, its distance from here, in a structure that you could have no control over. How do you even think
Yeah.
about this
Yeah,
circle?
we can construct a sequence like that.
Yes, exactly.
Sequence of radiuses.
How do you even think about this circle right now and its center? But
Yeah.
with this insane transformation that is apparently so magical and so simple, you were able to get such a ridiculous amount of control. Is the point?
Right.
And it's just a classic, perfect example of the power of inversion. That's why it has its own number file video as well. Okay, so now we'll look at a couple of very famous and common inversions that you'll often see. One is the orthocenter inversion. Anyone who knows the orthocenter inversion?
Root H HD.
Yes, perfect.
Actually 4r square cos A cos B cos C root.
Oh, don't, no. Does not matter what the value is, please. Do not spoil little kids with trigonometry.
I had read that, but I don't remember.
Okay, yeah, I have never remembered it. Okay, apparently we still have B and C, so let me just clear all. Don't save. Yeah, okay. Okay, close this. So what even is GGB thinking? GGB is going crazy. Sorry. Okay, finally. Let me actually draw the lines. This is crazy right now. Okay. So this inversion is root AHHD, as someone said, right? Did you say AHHD or did you say AEAC? I'm sorry, I'm confused. AHHD or HAHD? I'm curious which inversion you said. Both are good.
Like it was a Mayuk Chaudhary.
Yeah, which one did he say? AHAD or HAHD?
Yeah,
AHHD. I mean, it's the same.
AHHD. Okay. So what this inversion is, you invert from the orthocenter. Now you know that HA into HD is HB into HE is HC into HF, right?
Power of point.
I hope everyone knows this. This is just power of point on, as he said, on this circle, which is obviously which exists because AEB is equal to ADB is equal to 90. So inversion from H, you can take A to D. What you'll be like, oh no, but that makes no sense because the inverse is supposed to be here, right? So what we do is reflection as well. We'll reflect across H as well. We'll consider that as a part because we can say the radius was negative. Like the radius was
Actually, sorry.
imaginary.
Actually, sorry, but like when in starting you introduce inversion, you said a point is like a point is inverse with respect to a circle. But there's no circle, so with respect to what we are inversion.
I'll draw a circle if that's the case. Circle H.
So it's root H dot HAD or minus root H dot AD? No, HD.
H into distance H comma D. There you go. You have a circle.
So what is the circle? Like this is a random circle we are like for which we are inverting A with respect to.
We are taking the circle with radius root HA into HD.
Okay, so are there any nice properties, or is this like not a very research still to this?
No, this is a very nice circle. This is a very nice inversion. A goes to D, D goes to A, D goes to E, C goes to F, F goes to C, E goes to B.
Oh, okay, so I got you. Like, am I right? Like, the thing is that wanted to reflect from A to D, C to F, D to E, so we found such a circle.
Yes, because and
And the
that's
radius.
okay. This circle is important that it like you can find such a circle because HA into HD is HB into HE is HC into HF. This does not necessarily always exist. It's a
Okay,
very
and the radius of the circle is.
root HAHD. Why do you need to find it? There is
Okay, so is there anything special about the circle? Is what I meant to ask.
oh with about the circle, not to my
Yeah,
knowledge.
circles. Okay.
Like, is
No,
there any name
because
to the circle?
yeah, I don't know anything nice about the circle in particular, especially because the circle we'll actually do it with is root HAHD. We're not doing it with this circle per se, because now if if I told GGB, hey, reflect this point about this circle, GGB will like, oh, it's here. But we want it to be D. So when we are doing the inversion, we are pretending that it's a negative inversion. That A prime actually goes to the reflection of H over D as well.
So okay, so, yeah. So like, why did you go to tools and constructed a circle? Like you've directly done it through like reflecting about circle point. Oh, okay. So we actually needed a circle first. Right?
Yeah, but like, how does the circle matter? The circle's radius matters, right, to us.
Yeah, that's it.
How does the circle even matter? Where the circle is, what it's doing. But yeah, the circle should just exist. We should be able to do this, is all. Now you're asking why this inversion is nice, correct? Why it makes sense to
The
do.
inversion is nice because A goes to D, B goes to E, and C goes to F as you told.
Yes, but what else?
What?
For example, this circle goes to like just like this line now. This line goes to this circle. So
Basically, orthogonal inversion is you invert and then reflect about orthocenter. These two functions combined, right?
yes, but when we can include orthocenter like reflection while doing it. So what we'll do is here, if you think of it as directions, like if I make this HA, now if you think it with directions, HA into HD makes little sense because HA into HD is negative, right?
Yes.
Because they both are in opposite directions, so the value is supposedly negative. But then what does the square root mean, right? So the circle will actually be imaginary if you think of it that way. It's called a negative inversion for that reason. But the point is, when you do the inversion, it makes sense because you're just including the reflection already in the inversion.
Okay.
Does this make sense to everyone?
Yeah.
I don't think so. That will be.
So I think that you should replace it with AH again.
AHAD? Why?
So AH again, like in that inversion handle, overly.
No, HAHD is better because you're inverting from H. So the lengths from H matter.
Okay.
So they should be both in opposite directions. That's only why what I'd done before was wrong.
But basically, why did we like? What was the benefit of this?
The structure is preserved a lot. See, like this circle which we had goes to this nice line. Now, if say you wanted to intersect some, okay, I'll show you an example problem. Let's say, okay, does anyone have a random problem they can share? Oh, what should I tell?
For
Okay.
Inversion.
Of orthocenter inversion, fine. I'll show this. I don't know if this will be too heavy, but sure, we can do this since I already have the whole diagram set up. So I did my root HDHD inversion, correct?
Yeah.
So where does this point go, which is the midpoint of BC?
It will go to the circle ABC and the midpoint of AB.
Midpoint of AB?
Oh, RKB.
Midpoint of
Not
RKB. Why?
Oh.
I mean, why is it even asymmetric? Why would it be?
Okay, so just to be clear, we had reflected BC and then we got the circumcircle of AFHE, right?
Yes. That is a property because just B and C go to E and F,
Yeah. Okay.
and lines goes to circle through H. So it becomes a circle EFH. And okay, D also goes to A. So yes. Very simple. We know like line BC goes to the circle this. So it goes to this circle, correct? It also
Yeah.
goes to a point which is on line HM,
Yeah.
correct? So it's HM intersection this circle. But it also seems to lie on this. Why?
Because like ABC goes to DEF, which is the 9-point circle, and DEF passes through I. That's why.
Good. So earlier we had DEFI are cyclic. So inverse of this goes to ABC because E goes to B, F goes to C, D goes to A. So the 9-point circle goes to ABC. So you even got that EF and G cyclic. Very nice property, very simple through inversion. You got HM, EHF, and ABC concur. Nice property, so simple through inversion. Some hint for buffer problem A. Right, I'll give hint based on my solution. Try inversion at A or D, or both.
I tried inversion at A and Z, but none of them seem to work nice.
Try at A and D.
Okay.
That's what I did. I did 2 inversions, A and D.
So is it a composition of inversions?
Yeah, first inversion at A happens, I think, then inversion at D happens.
Okay.
Okay. So this is your structure, such a nice property, proved easily. It also proves the existence of the 9-point circle in a way, but okay, let's not pretend that happens. If you knew this property, it does that. But of course, this 9-point circle is a much more basic property. Okay, is this much clear? Why this is nice, I think some of that might also be clearer now. It would be great if you could answer.
Yes.
Yeah.
Thank you. That's very nice. Okay, now that we have this out of the way, let's look at another nice inversion. Oh, wow, we spent a lot of time. Okay. Did not expect this to go this slow. Okay. Next is in circle inversion. We'll look at this problem for that. Can anyone try this first?
Okay, sir. Didn't get the chance to see the problem.
Okay.
Can you show it again?
Okay, I'll just tell you the problem. You have DEF as the contact triangle. Contact triangle is the triangle made by the touch points of the inner circle. You have H is equal to the orthocenter of the contact triangle. Prove that HIO collinear. This is the problem.
If we consider the composition of inversions, isn't the image of Z not very weird?
I'll not be discussing that right now. You can think about it. Otherwise, you can try the other buffer problem if you're getting confused.
So, does the order matter? First inversion at A, then at D, or is it similar?
It matters. It matters. It matters a lot.
So, what was the order?
You can find it. Try both. What makes sense to you? Which do you think is nicer?
I mean, have you given some question? I was just disconnected.
No, I gave the buffer problems in the starting for those who are familiar with the content.
No. What? I just got disconnected for 5 to 10 minutes.
Okay. So ABC is a triangle. DEF is the contact triangle, like made by touch
Yes,
points
yes,
of
yes.
a circle. O is circumcenter, I is incenter, H is orthocenter of DEF. Prove that OAH collinear.
Acha, I've done.
Yeah, okay, just anyone who's not very comfortable. Okay,
Can you once repeat that? Like, like if it take 2 minutes, that when does a circle go to some line?
when does a circle go to some line? When the line passes through when the circle passes through the center.
Okay, so I mean, I got an idea. I don't know if it's correct or not. So if I can prove that, wait, no, it's bad.
Okay, so we invert about the in circle. Okay, when we invert about the in circle, where does A go? Where does A go when you reflect across when you invert with the in circle?
Midpoint of EF.
Good. Can everyone see why?
No.
IA prime is IA prime into IA is IE square. That's just because IA prime E is similar to IEA.
Oh, okay.
Yes, yes.
Similarly, you get B goes to midpoint of okay, why does this not work? B goes to midpoint of
No, you are reflecting across DF instead of
okay,
that circle.
my bad. C and C goes to C prime. Okay, good. And let me delete this extra points that I've generated. Okay, good. Now you get A prime, B prime, C prime. So where does the circle go? ABC circle.
A prime, B prime, C prime. The
Good.
9-point circle.
The 9-point circle. Very good. Of DEF. So where does the center go?
Between H and I.
Midpoint of HI.
Yes.
Center goes to midpoint of HI?
No, center of the 9-point circle.
Yeah,
No. Where does the center of O go? Like where does the center of ABC go?
On the Euler line of the contact triangle.
9 center of.
No, the circle's center does not go to the other inverted circle center.
O goes to some point on the Euler line of the contact triangle.
Why?
Because we are inverting at I.
So
no, like I mean, it will be on the line HI, and that's what we care about, right? So it will be on the
yeah,
line HI, and 9-point central center will be on the line HI.
we want it to be on line HI. Yes.
But by inversion, it will already be on line HI.
Why? You say OI and 9-point center of this circle are collinear. O prime, I and the 9-point center are collinear. OI and 9-point center are collinear.
Yeah.
Okay. OI and 9-point center are collinear. You know that I 9-point center and H are collinear. So HIO are collinear.
Yeah, that's what I'm doing.
Good. Does everyone follow? Everyone knows that HI and 9-point center are collinear, right? H is orthocenter, I is circumcenter, orthocenter, circumcenter, 9-point center collinear. Good. That's the entire problem. That's it. So that's why this inversion is also very nice sometimes.
So why 9-point circle I and O are collinear? 9-point center I and O.
Because inversion takes the center to a point on the same line.
Okay.
Centers are collinear. The inverse of the center of the inverted circle original and the center of the original circle are collinear with I, like with the center of inversion. So this also shows you that the circle ABC goes to the 9-point circle, which is also nice. Okay, we have seen two properties, and the third nice inversion is the root BC inversion per se. So we have noticed that in a few of these diagrams, one thing, why are we doing these inversions that are nice? Why do we think like AD, like root AHHD was nice inversion? Root HHD was nice inversion. Or why is this in circle inversion nice?
Okay, so like known points go to known points, I guess.
Good.
And there is also a lot of intersections and stuff.
Good. You are able to overlap a lot of the current diagram with the new diagram. Is a thing that's appearing, right? Like DEF was in the original diagram, and you're able to overlap it with the new diagram as well. And you're able to think of much more things. And in that also, like A, D, B, E, C, F all were preserved. And it was like a very nice overlap with the well-known diagram. That's a very common theme of why you should invert and when you should invert. And that's what we'll do in the final inversion, which is the root BC inversion. We'll forcibly force things to go to where we want them to go. If I do root BC inversion from A, why should it be nice?
It will send B to C.
How? It will go to some point on AB, dude. How will it send B to C? B will go to some point on AB.
Isn't root BC inversion like after reflecting across the angular vector also?
No, I mean root BC inversion and reflection, you mean, no?
Yes. Okay. So basically, it will go to a point on line AB with the same distance as AC.
Yes, but that in itself is not nice to us because it does not overlap. So what we do is force it to overlap. We invert over the angle bisector. Sorry, we reflect over the angle bisector as well. Do you understand what we did? Okay, like we
inverted with root ABC and then reflected along the angle.
Good. And that's very nice again to us because we were able to preserve a lot of the structure. We were able to preserve, we sent B to C and we sent C to B. And that overlaps with our original diagram a lot. Correct. And so now all of our old issues will become very nice again. Like this, the circumcircle of ABC will go to the line BC now. And we are able to talk about a lot of things again. Because there's an incredible amount of overlap. Does that make sense?
Yeah. Yes.
Okay, good. Now that we have that out of the way, you can read these properties as well. B maps to C. Okay, B maps to C, C maps to B. This is what it's supposed to be. BC maps to ABC.
O maps to H.
O maps to H? What? No.
And the fifth one.
No. O does not map to H. No.
Oh, sorry. AH line maps to AO line. I meant.
Yes, I mean that's just reflection over angle bisectors. Yes. I maps to, like in center maps to AX center. AX circle maps to a mixed linear in circle, whatever that means. And there are many other nice maps which you can try to figure out. And I've written, okay, you can prove these on your own, right? You can also find the distance formula. It's very clean of what AB goes to.
Yes, just for similarity.
Yes, just direct similarity, yes. Now, when you have that, try this problem, of course, Ptolemy's inequality. You can easily prove this. There's nothing much to do here. Okay, so we have, okay, can anyone tell now when we should invert? Or what, anything that you've noticed on how when inversion is good?
Yeah, like one point is very clear that we know that when a circle passes through the center of inversion, it goes to a line. So this is a very important thing.
When
Like
many
when you have circles or you just don't know what to do.
you just don't know to do, so let's invert.
Like there is not
But
much to prove in the original problem, so you try to invert.
When there are lots of tangency conditions.
good. Many tangency slash parallel conditions. What else?
Many circles pass through a single point.
We have written that.
Oh, okay. Uh, and like a famous point maps to a famous point. I mean a known point.
When there is when there is a lot of overlap with the original diagram. Okay, what else?
And orthogonality.
Orthogonality, you're preserving circles. That's just overlap, right? That's the same thing as this. That's mostly it. That's mostly it. When many lines are randomly there, okay. Subsection. When not to. Item. And okay, develops as intuition. Intuitively makes sense too.
The Olympiads make such problems which can only be solved by inversion.
I don't think you can say only by solved by inversion, because you can literally repeat the whole argument with angle chase, because
Yes, yes.
every
Because
argument of angle inversion is angle chase. So you can go through it in the reverse direction as well.
and also there are possible some problems which don't seem to work with inversion, but there exists a magical solution with inversion.
Yes, that is just your intuition. It will tell you if you practice more and more when it seems to be good, when it seems not to be good, when not to. This this section again,
Too much
not
lines.
strict, not a general statement, might actually end up being a good idea too in some problems. But
Do the place
many
command
random
works in
lines.
overleaf?
What command works in overleaf?
To replace.
So yes,
What's the shortcut key?
Control F, like always.
Okay, control F. Okay.
Many random lines not passing through same point. Sometimes you actually want to invert to get circles, which is weird, but yeah, that's also a theme that happens. What can you do about it? Like, remember, how many of did any of you attend Pranjal's OMC lecture on conics?
Yes.
So
Yes,
there,
yes.
in one of the problems with the Clausen conjugate, we wanted
Yeah.
to invert even though there were lines to get the Mickel point. So sometimes you want to, but when many random lines not passing through same point are there. What else? When you have angles which are not through same point, not through the same. When the angles are not through a single point, maybe. Yeah. Okay, this comes with disclaimer. You can still find them. For example, if I wanted to find angle BCD, how do I do it? In the inverted diagram, what is BCD? Where B dash is inverse of B, C dash is inverse of C, D dash is inverse of D. What is inverse of angle BCD?
C dash B dash A plus C dash D dash A.
Good. So you can simply just break it down into two parts, including the center of inversion. BCA plus DCA, and BCA goes to C dash B dash A, and ACD goes to C dash D dash A. So BCD becomes C dash B dash A plus C dash D dash A. That's also fine. Sometimes this way of working it might end up being fine, and some random angle sums which involve A might actually come together. So those are things which come with a disclaimer, but when you have like all of these angles being so weird because it splits into two, it might not be a good idea. And the things you want to prove are very angle based. Is this fine?
Yes.
And this type of breaking into two angles, moving them here and there, and then doing stuff is not very uncommon in with inversion. Okay, did someone actually? Okay, distance formula actually rarely comes up, to be honest, but yeah, it's also possible that it comes up. I've seen it a couple places. Many perpendiculars. I do not think perpendiculars are that nice a condition, in fact, because inversion might spoil them. But sometimes, of course, it's nice. I mean, random 90-degree, it will just spoil, right? Like if BCD was 90, it's now a B A C dash plus A D dash C dash is 90. How's that nice? Yes. Again. Okay, fine. This shows many angles or makes them nicer. Is okay. Weird sentence, but okay. This is similar to this. Okay, that's mostly it. Otherwise, it's just you'll know with practice when it's good, when it's not, where you should be inverting. Also, people have different intuitions. Like when I think you should invert, Pranjal might not. When Pranjal thinks you should invert, I might not. It's different from person to person as well. There
Are
might
we done
exist
for today?
what?
Like, is it is this lecture finished?
Uh, mm, should take 5 more minutes?
Okay, fine.
Okay. Any doubts till now, or anything you want to ask or say?
We are not gonna do problems.
We discussed shoemakers. We discussed this
No,
problem.
like some real Olympiad problems.
This is also from Olympiad only. This is not something like this actually came on a contest. But otherwise, I've given you 10 practice problems. You can try them. Okay, we'll do one problem. Fine. We can do an INMO problem.
Yeah. Okay. Okay.
Sounds good?
Yeah.
So INMO,
What?
like INMO or IMO?
INMO, INMO.
Okay.
What is the problem number on preset?
It's not in the P set.
Ah. Oh, can we try the problem later and ask out now?
Yeah, of course.
2000. Is it a 2019 problem?
2019, yes.
Okay.
I assume you're familiar with the problem and the proof then.
Yeah, I have seen that some time ago. I don't remember that one.
Okay. Can
Can you tell problem number once if you know?
I put it in the chat? The problem is there in the chat.
Oh.
Okay, why is this not working? Okay, cool. Foot of perpendicular. How do we draw foot? Yes, yes, perpendicular line.
This is 2019 perhaps, no?
Yes, yes.
I mean, it can be done with just part of point stuff.
I mean, the power of point argument is the inversion argument.
Yes, without stating the word inversion.
Yes, of course. Okay.
Also, which problem are you guys not able to solve this year? INMO.
I
Yeah.
I
Okay, that geometry one.
yes.
You scored 85, right?
Yes. Mm. Okay. What am I doing? This makes no sense. Yes, this. Okay, I'm being crazy. Fine, ignore this. Yeah, what were we supposed to do? Yeah, this con. Because he was bored, or else he would have. Exactly true.
Oh, were you able to try P5 or time finished by the way?
I had half an hour, and I was lazy. Yeah. So
Almost
I
the
just
same thing, no?
fixed the other ones.
So, like, can you give a number?
What do you
Like,
mean?
till now, how many problems have you solved? Like, a upper bound will work.
No way.
Like 2000?
No way.
No,
I
no,
have
no.
no
Like,
idea.
just give upper bound. Just give upper bound.
I have no idea. I'm not even going to conjecture. I have no idea. Okay, we can just do it this way. I'm being crazy, so crazy. Fine. Okay, and I want this, so I do this. Sorry for the delay. I want to make an accurate diagram for some reason that I do not know. I have not done an accurate diagram in so long.
Upper or a lower bound, or like any guess.
No. None at all.
Like a very lower bound, very weak.
No, no. Yeah,
लोअर बाउंड क्या
3. Yeah, okay. Finally. Let's. Yes, okay. This is the problem. Finally, we have it. K is of such a point. This is H. H is such a point that the semi HD is AC. Prove that the X circle of AHD is tangent to ABC. Okay. So, can anyone tell the proof now? This should be very clear from if you from you've done inversion.
Seems like root BC inversion.
Root BC? What?
Like because there is an X circle.
So
He said root BC.
yeah, I know. You want maximum overlap with the initial structure. Correct?
Oh, what is this big one circle? Like center A and passing through C?
Does not exist. Let me hide it. Does not exist. Yeah. I've drawn the full diagram. I've given every hint is there in the diagram. You know inversion, you can do this.
Center A, radius root AH into AD.
Why?
It sends D to H and H to D.
Sure. You'll also reflect across angle bisector. Fine. Where does this circle go? Don't know, right? It's weird. It's hard. No point in doing this. What's nice? Why is the semi-perimeter of HD nice?
AC will be equal to AE or AG.
Exactly. We know that the semi-perimeter
Yes,
is the
yes.
distance of the length of the tangent to the X circle. Correct? Everyone knows this, right? If you don't, AG equal AE and AG plus AE is AH plus HG, which is HI, plus ID, which is DE, plus DA. So that's AH plus HD plus AD, which is AG plus AE. So AG or AE is half of them with half of perimeter, which is semi-perimeter. Good. So now AG equal AC equal AE. Now what do you do? What do you do? Come on, come on. Where is someone tell?
Someone wrote in chat invert about AAC radius.
Brilliant. That's it. You invert with center A with radius AC. What happens is this circle gets preserved because AC equal AG equal AE. T stays at C. D goes to some point here. D goes to B, right? Because AC into AD, AC square is equal to AD into AB. Because ACB is 90, ADB is 90, angle CA.
Yes.
So line CD goes to circle ACD. But we know tangency is preserved. If tangency is
Yes,
preserved,
yes.
this line and this whole circle were tangent because X circle. Then this circle and this circle are also tangent because this circle was preserved. And we are done.
Basically, the idea was to use the equivalence in a nice way.
Yes. And that's it. You can also repeat the argument by power of point. You can say you can argue AJ into AK is AC square. Now you can argue that AJ into AK is equal to AC square is equal to AE square. So K lies on the circle, and then you can argue tangency that AKE is JEA, and you're done. That's the same argument if you want to do it that way. Okay. Good enough?
Yes.
Yeah, two linear. Basically, inversion just kills it completely. AC equal AG equal AE because AG is equal to AE is equal to the semi-perimeter. Invert with center A and radius AC. The line CD must go to circle ABC because AD into AB is equal to AC square. So but the circle X circle is preserved. The X circle is tangent to ABC, and we're done.
Yeah. This was very nice.
Yeah, it's a.
Isn't this a bit easy for a P5 by the way?
Nice
It's
to
an
learn.
INMO problem, not an INMO.
It's a P5. Even more.
INMO is not difficulty ordered, if you are aware.
Okay.
Also,
Yes, it was not difficulty ordered.
yeah. Thank you all for joining.
Do we have any class after this?
I'll start at 7:15. I think many people agreed to that by an overwhelming majority.
7:57, 15 to 10.
Roughly, yeah. And we'll have breaks in the
Yes.
mid every half
First,
an hour. So
first there will
And
be a
we-
PSS.
PSS
And any
then
class between 6 and 7:15?
nothing. We can we delay 20 minutes. We'll start at 7:30 to 10. Okay.
Thanks for this.
There will be first a PSS, then projective geometry.
Correct.
Okay, thanks a lot.
Yeah. Thanks for
So
joining.
like PSS will include what?
Problem solving.
No,
section.
geometry.
Geometry. Yeah.
Yeah, problem solving for sure.
Yeah. It's all in the schedule. Thanks for joining. Pranjal, you can stop the stream.
Thanks for the class.
Yeah. Thank you.